What's up, everybody? Welcome back to Mathlete's Corner. In this video, we are going to move on to Logarithms Level 5. So hopefully these problems are a lot more challenging than any of the other problems that we've seen in this series so far. And something to just note is that logarithm problems at this level generally don't solely rely on logarithmic properties, right? So we usually need skills from other topics to help us tackle these problems. So with that in mind, let's get right into it with our first problem being the 2019 AIME 2 problem 6. And so we have this Martian civilization, and all logarithms whose bases are not specified are assumed to be log base b for some fixed b more than or equal to 2. And a Martian student writes down these two equations here and finds that the system of equations has a single real number solution x more than 1, and we have to find b. So first, looking at this second equation, we see that we have that nasty log x as a base itself. So let's try to get that out of there. We don't want logarithms in the base, right? We want to deal with logarithms base b, since that's the base that we want to look for. So if we get rid of that, if we convert it to exponential form rather, we get x is equal to log base b of x to the power of 54. And I'll write the base of b just for clarity so that we know what we're solving for later. Now, we have a formula for x, and what we see in this equation is that we have a root x. So, if we were to write root x in this form, we would get log base b of x to the power of 27. Now, if we plug that into the first equation, we get 3 times the log of log base b of x to the power of 28 is equal to, and I believe it is 56. Now we have that pesky 3 on the left hand side, so we can move that into the exponent. We get log base b of log base b of x to the power of 84 is equal to 56. And once again, we have a logarithm in the wrong spot, right? We don't want a logarithm inside the parentheses. We also don't want logarithms in the bases, so we can convert this into exponential form again, and we get b to the power of 56 is equal to log base b of x to the power of 84. Now, obviously, these exponents are fairly larger numbers, and we can notice that they're both divisible by 28. So we get b squared is equal to log base b of x to the power of 3. Now, if we go back to our equation for x, we also have x in the same form. We have log base b of x to the power of some exponent. If we use this in our equation for b, we want to find an exponent of 54 on the right hand side. So we can take both sides to the power of 18. We get 54 on the right. On the left, we get b to the 36, and we know this is equal to x. So long story short, we get b to the 36 is equal to x. So what does that mean? That just means that log base b of x is equal to 36. And now we can actually plug that back into this equation, and we get b to the 36 is equal to 36 to the power of 54. And then if we take both sides to the 18th root, we get b squared is equal to 36 cubed, and b is equal to 6 cubed, which is 216. So this problem specifically happened to solely rely on those logarithmic identities, but in the next problem that we're going to see soon, we have to use some other skills. So let's get right into this problem. The 2017 AIME 1 problem 14. It says let a more than 1 and x more than 1 satisfy this hideous equation and this less hideous equation. And we want to find the remainder when x is divided by 1000. So let's focus on this less hideous equation because obviously it's easier to work with. So when we convert this into exponential form, we get a to the power of 256 is equal to x. Now we can focus on this more hideous equation now. And when we simplify that, we get a to the power of 128 is equal to log base a of log base a of 2 plus log base a of 24 minus 128. Now, we'll just keep simplifying and keep converting into exponential form. So if we continue that, we get a to the power of 128 plus 128 equals log base a of log base a of 2 plus log base a of 24. And we see here that we can convert these logs actually into log base a of 24 log base a of 2. Now we get a to the power of 128 plus 128 is equal to 24 log base a of 2, and that is equal to log base a of 2 to the 24. And we want to bring that 24 into the exponent because otherwise it'll be in the exponent of the left-hand side as a denominator, and that'll be really nasty. So now that we have this more simplified form, we can turn it into exponential form one last time, and we get a to the power of a to the power of a to the power of 128 plus 128 is equal to 2 to the power of 24. Now, here, it would be really nice if we didn't have that addition there in that last exponent up there at the top. So let's try to split that up. So when we do that, we get a to the power of a to the power of a to the power of 128 times a to the power of 128. And now we got rid of the addition in the exponent, but now we have this multiplication in the exponent. And so to get rid of that, we can just convert this into a to this power. So a to the power of a to the power of 128 to the power of this. So we can take that to the exponent. And here we notice that the base and the exponent are actually equal. And remember, this is equal to 2 to the power of 24. And if we do some experimentation with this value, 2 to the power of 24, we see that it's actually equal to 8 to the power of 8. So we see that a to the power of a to the power of 128 is actually equal to 8. And that is so much simpler. So what we just did was clearly very clever. But what if we could do that again? Bringing in that wishful thinking. Well, here it's much more difficult to realize how we can do that since we don't really have a lot of repetition, right? We can't make the base and the exponent equal that easily. But what we do notice is that we do have these two a's. The only thing that's remaining is the 128 in the exponent. So what if we took another exponent of 128? So let's try using that. So we have a to the power of a to the power of 128, all of that to the power of 128. That is equal to 8 to the power of 128. Now, instead of keeping this exponent on the outside, let's bring it to the inside. So we have a to the power of 128 times 128, and that's equal to 8 to the power of 128. Now we can repeat what we did earlier in the problem, and we have this a to the power of 128, and that value to the power of this exponent. So here we put another a to the power of 128. This is equal to 8 to the power of 128. And after some experimentation, we notice that is just 64 to the power of 64. Now we see that a to the power of 128 is equal to 64. And from this equation, we get that a is equal to 2 to the power of 6 over 128. Obviously, that exponent can be simplified to 3 over 64. Now, in the very beginning of the problem, we found that x is equal to a to the power of a to the power of 256, and this is where we use that fact. So now we can plug in our value of a, and we get that x is equal to 2 to the power of 3 over 64 to the power of 2 to the power of 3 over 64 to the power of 256. Now we can keep that base the same for now, and the exponent just becomes 2 to the power of 3 times 4. So the exponent is just 2 to the power of 12. So we have 2 to the power of 3 over 64 to the power of 2 to the power of 12. And that's just 2 to the power of 3 times 2 to the power of 6, which is 2 to the power of 192. Now we've found our value of x, and we've basically completed the main portion of the problem. But we have to remember that since it's AIME, they want us to find the remainder when we divide x by 1000. So for that, we will be using the Chinese remainder theorem and Euler's Totient theorem. So I recommend that you take a look at those theorems before you come back to this part of the video. So for our Chinese remainder theorem, we can split our mod 1000 into mod 8 and mod 125. And we know that in mod 8, we just get 0 since this value is clearly divisible by 2 to the power of 3. Now we have to find the remainder when we divide by 125. So for this, we will use the Euler's Totient theorem. So we can say that 2 to the power of totient of 125 is congruent to, and obviously the totient of 125 is just 100, and that is congruent to 1 mod 125. Now from this, we see that 2 to the power of 200 is also congruent to 1 mod 125. But we have to remember that x is 2 to the power of 192, which is obviously less than 2 to the power of 200. So we can write 2 to the power of 192 as 1 over 2 to the power of 8. That is 1 over 256. And since we're in mod 125, that is congruent to 1 over 6 in mod 125. So essentially, all we want is the inverse of 6 in mod 125. Now, since 6 is a factor of 126, this is actually fairly simple, right? The inverse of 6 is just 126 over 6, which is equal to 21. So now we know that x is congruent to 21 in mod 125, and x is congruent to 0 in mod 8. And combining these two parts gives us that x is congruent to 896 in mod 1000. That's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button. For another cool AIME logarithm problem, click on this video right here. And we'll see you next time here at Mathlete's Corner.